Then I need to join audio. Sorry, you know what? I messed up because I'm on the wrong machine. Oh, that's awful. Sorry, I now just need to turn. There we go. Okay. I'm really sorry. Well, that's okay. I'm really glad that the conversation went on about something more important. Happy birthday, Zach. So the there, that should work, and I think I am recording now. I want to make sure I'm recording. Oh, come on. I just want. Yeah, okay, it's recording. Okay, good. Well, this is gonna be a really awkward beginning, but I can't be bothered to try and edit the videos because that takes quite a long time. So you're gonna get this weird trying to figure out a computer thing going on. Anyways, oxymercuration, demercuration, then we're gonna bring up a couple Mobius questions and talk about those. So oxymercuration, demercuration solves a problem. The problem is, what if, okay, I'm going to show something where it would matter. So you have a real world example is beyond a little bit beyond the scope of the course. So if I had a molecule like this, and I wanted to make, yeah, there's silicon, don't worry about it. Silly atom. And I wanted to make that. If we're looking at that, we're thinking, hopefully you're thinking, I'm trying to do a Markovnikov addition of water. And the way I do a Markovnikov addition of water is I add an acid of my choice, and I add water, and I get my product. Except you don't get that product. You do the Markovnikov addition, which is great, but then this silicon thing falls off. The problem there is that this guy here is acid sensitive. So in the presence of acid, this thing falls off. And so for all the Markovnikov additions of water we've seen have involved acid. So there's the need, and a lot of molecules are actually really acid sensitive, things like DNA, a lot of sugars, way too many sugars, amino acids, all sorts of different things out there are really, really acid sensitive. So you want to avoid using a strong acid, but you can't do the Markovnikov addition without the strong acid. Okay, so that's where this oxymercuration, demercuration thing comes in. So this is on assignment 2. So I'm just going to do this guy. And the reagent is mercury diacetate in water. Now mercury's, no, the oxygen stays behind. Just the silicon falls off. The oxygen's still there. Normally you need to, what ends up happening, anyone who's for some reason is working on this kind of thing in silicon chemistry, is a water molecule will come in and interact with the silicon as well. So the silicon will have a water attached to it, but not that water. Okay, so we have this. And what we're going to do shouldn't surprise anybody. Mercury diacetate is that. And for those who don't remember, and I know you've seen this in Gen Chem, acetate is this thing. Oh, happy birthday to you too, Kristen. Hopefully it's a happy birthday. Hope springs eternal. Damn it, you piece of shit. Sorry. What should I do? There we go. So, we have this. This is now going to attack the mercury. The mercury is going to lose one of the acetates. Different example, I left the silicon off because it just complicates things. You would only do this in that kind of case. With this molecule, you would use acid and water. But, you know, just more drawing, and it's not, doesn't affect the mechanism. Oh, look, it's a 3-membered ring. So you got this mercury. It's a 3-membered ring. Mercury is delta positive because it's a metal compared to these other guys. It has to be delta negative up here because it's an acetate and not a metal. That is not an ionic bond. That is a covalent bond between oxygen and mercury, but it's a very polar covalent bond. Now, if you have a delta plus with a 3-membered ring, this behaves exactly the same way we've seen 3-membered rings with delta pluses behave for the last few weeks. So what else is present? Well, there's water. And so the water comes in, and it comes in exactly where you expect it to, the more stable carbocation, because again, partially positive mercury, pulls electrons away from the carbons, and I get something. And you get the precise mechanism you would get if that mercury was a chlorine instead, or a bromine, or a protonated epoxide. So it's all the same. There's nothing new here. And we have a neutral mercury. Now, what happens? Because there's mercury on this and this is positive. So the first thing we need to do is we need to deal with that positive charge, get rid of charges. How are we going to get rid of that positive charge? Well, I'm going to just draw the H's explicitly. We do have some acetate floating around for the mercury. It's a weak acid. We could use that. You could use water. You could use... No, I think those are your two options. You got water and you got acetate. Either one works. Note that the oxygen has come in the hydroxyl group is anti to the mercury. It's exactly the same thing as we've seen with every other types of these 3-membered ring attacks. There's nothing new here. Okay. This is stable. You can isolate this. You can play with it in your hands. I wouldn't because it's got mercury on it and it's pretty toxic. And mercury metal is bad for you, but organomercuries are really bad for you. So this goes straight to your brain and kills you. So you probably don't want to play with this, but you can if you want to. So what we normally do is we flip the page, because we're out of space. Is we add a reagent called sodium borohydride. And this is often done in a methanol solvent, or ethanol, or something. Doesn't really matter. Okay, let's just think about this sodium borohydride thing, because we're actually going to be talking a lot about it in the next few lectures. So what does that mean? Well, it means sodium plus, BH4 minus. And what's that? Well, that's B with 4 H's. So again, we're coming back to this boron chemistry that we had talked about, where we've seen BH3 already. We saw it with the hydroboration. This is BH4 minus. And that means that the boron is formally negative. It's got 8 electrons, but it would like to be neutral, but it goes down to 6 electrons. So what this is a source of, really, I'm going to draw it in brackets because you don't get H minus. But technically, this is a source of H minus. Now, H minus, when it's covalently bound to something, and we're going to see a few other examples of this, but here's covalently bound to the boron, acts as a nucleophile. Not a base. I don't completely understand why. I think there's been a lot of thinking about this. You can start drawing all sorts of molecular orbitals and talk about the energies of those things and justify this. Sure, I'm not sure how much I believe it, but the proof is in the pudding. It acts as a nucleophile and not a base. So what happens if we have a nucleophilic H minus? Well, what we end up doing, if you want to think about it, this guy loses H minus. It attacks the carbon with the mercury on it, because the mercury, again, that carbon-mercury bond is very polarized. The mercury is very positive. Double apostrophes, I'm putting that in like scare quotes, because it's not a real, it's not really doing that. It's just, you can think of it that way. So it's not really BH3 and H minus. It's not really in equilibrium with that, but it kind of acts a little bit like BH3 and H minus. And that's what we're seeing up here. And then we're going to also lose the acetate because now mercury's received electrons. And if we're keeping track at home, the new hydrogen has to have come in opposite the face of the mercury. What else do we have? Well, we've got mercury, metal. Those of you taking inorganic, and who have the exam on the exact same day as this one. I think the inorganic exam is in the morning and the organic exam is at 7 p.m. at night on December 12th. Yay. If you count your electrons on, yeah, exactly, can't wait. If you count your electrons, now Marcus and I had a conversation about this in the hallway, or Dr. Drover and I had a conversation about this in the hallway. And we were told in no uncertain terms that what we were not to do is to poll the class and ask the class if the class wanted to change the date of the final. But we were told that should a member or a group of the class come forward and request a change in the date of the final, that we could forward that request onto the registrar's office to have the final date changed. And the final dates that we were definitely not told to consider were, I'm just going to pull them up. Oh, come on, they've got this. December 18th at 3:30 p.m. or December 21st at 8:30 a.m. or 3:30 p.m. So there are options to change it to, so if anyone didn't have a chance to write that down and wants to note that, the dates that exams can be moved to at this point are December 18th at 3:30 p.m. or December 21st at 8:30 a.m. or 3:30 p.m. So what I need to have is, I recommend those of you in the inorganic are probably going to bring this to Dr. Drover, because I don't know if there are a lot of conflicts, and if there are any conflicts with existing exams, they won't approve it. I don't care. I think this is insane that you have 2 chemistry exams on the same day. But I'm definitely not allowed to poll the class and ask if any of you wish to do that. Okay. What I would recommend you do is gather a bunch of signatories, send it to my head of, or what I recommend you don't do is do not gather a bunch of signatories, do not send it to my head of department requesting that one of these exams changes its date. Yeah, the 21st is ecology. That's not going to go too well because there's a lot of you taking ecology, even if it is just give the name of this plant. I actually don't know what they cover in ecology. Anyways, so what we have here is we've displaced the mercury with this hydrogen hydride. Overall, what's happened? Okay, let's look at the overall reaction here. Number one, we added mercuric diacetate in water. That looks like it's one molecule. Number two, we added sodium borohydride in methanol. There's a lot of solvents that it works in. It can work in basically any solvent. You can actually do this in water as well. Just not everything's soluble in water, so you find you use a lot of organic solvents. And the end result is a Markovnikov addition. But no acid needed. So it's the acid-free Markovnikov addition. So if you have a reaction which is acid sensitive and you need to do a Markovnikov addition of water, this is a good way to go about it. Well, it's up here, the BH4s in the mechanism here. The sodium's floating around, but I'm an organic chemist, so I really don't care what the sodium's doing. This means in, it's with. So one involves, it's kind of like that's over that. So it's the reagent and the solvent. I could put a comma instead, maybe. The either or on this is acid with water, which will also give you that. But if you can't use acid, you can use this oxymercuration, demercuration. Yeah, 3 and 24 hours is the rule. Or 5 and 48, I think. So it's legal for them to have 2 chemistry exams on the same day. Okay. That's why I want to talk about the mercuration, demercuration. What I want to do now, so I'm going to post this as kind of like a mini one-off thing, is I want to talk about how to approach thinking about some of the Mobius questions, because I'm getting a lot of questions about that. And I think depending on your background and the school you came from and how that ran, you're either familiar in looking at these kind of nonlinear questions or you're not. And you're not familiar with organic chemistry for sure, but that's neither here nor there. You get the same kind of questions in almost any discipline. So I'm going to just pick one. You know what? I think the ones that we see a lot of was this family of questions. So I'm going to just copy, paste. Yeah, so in inorganic, you would yes, in oxymercuration, demercuration by mechanism, Anita, they have to be trans. Yeah, the next Mobius assignment is not until the 27th. I just want to go over the current Mobius assignment. Or the one that we just did. But yeah, no, the next one, there's no rush to this. I felt we kind of rushed between the last two. The next Mobius assignment is kind of like sort of a final check before the exam period. Everything's on the Mobius assignment. Yeah, we already covered Markovnikov additions to dienes, Emmanuel. They're the same as Markovnikov additions to monoamines. For changing the exam date, I think what you'd want to do if we're inorganic is have a bunch of the people in the class co-sign a letter to the head of the department requesting a change of the exam date, saying I've got exams, 2 exams on the same day. We'd like it, if at all possible, for the exam to be changed. Okay. So this question, I think I labeled these A, B, C, D, whatever. And the question was, which of the following, and you could select more than one, represent the same structure as this one. So on the final exam, there will not be any multiple choice, which basically means it's infinite choice. Whenever you're approaching a multiple choice problem and you've got stuff like this, where you have the option of eliminating, ruling out things or ruling in things. And so I think it was which of these are the same and in the lowest energy conformation. Only your top 3 Mobiuses count, and if you do better on the final than your Mobiuses don't count. Okay. So, yeah, exactly. You win. The goal is for you to win. What I think you should do on this is the point of the Mobiuses. I've got, I'm recording this, so everyone's going to hear this, and I'm perfectly fine with telling you this. The point of the Mobius is so that you stay on top of the notes and stay on top of the problems and practice all the way through. They are grades. They do count. You do well. You got money in the bank, and that's great. Because the problem is, for everyone who's upset about their Mobius, and I know a lot of you are, and I figured out how to regrade it. So I'm going to go back and regrade the questions from the Mobius as needed. You're going to be a lot more upset if you hit the final and it whacks you over the head and you're not ready. And so where we found is that if there isn't these kind of things throughout the course, I used to do assignments not for grades and throw out all these assignments, like tons of assignments. And people didn't do them because they weren't for grades. And then they got to the final exam and they had put it off and they put it off and they put it off. And then they tried to cram the course in 48 hours and it didn't work. And then they failed the course and it was bad. Like, the material is difficult, I agree. But that means you should probably get on top of it sooner rather than later. And what the Mobius assignments do is they give you a reason to get on top of it sooner rather than later. And to practice and figure out what you're good at and what you're not good at. And hopefully you're doing that through the problem sets. So you're trying the problems in the book, you're trying the problems I'm giving you guys, and you're going, oh, I do not understand this. I need to learn this better. Or, okay, I got this. I'm fine with this. Now, if we're coming down to this guy, how do you approach this question? So the question asks you for these guys in the lowest energy conformation, and which one's the same molecule. So what we need to first figure out is lowest energy conformation. So you're looking at this guy, and you have some options on how you approach this problem. One thing is you could look at A through E and say, well, which ones do I want axial and equatorial, which one, and the other way around. The problem is if I look A through E, there's kind of like a whole mix of things, and it doesn't all make sense. Like A and B both have 2 equatorials and 1 axial. Like the methyl group and ethyl group are equatorial together in both those cases. But then in D, one's axial, one's equatorial. In C, they're both axial, and in E, everything's equatorial. So if you quickly jump to which one of those is the most stable, of course you're going to pick E, because E has everything equatorial. The problem is that the same molecule as the one I drew? So you've got a bunch of ways to approach this. One thing you can do is lose your slide. Where'd it go? Keep annotations. I have no idea where I am. There we go. Is take A through E and draw them out as hexagons. And so if I do that, that's A, that's B. I'm trying to keep things in more or less the same places where they are. and so forth. So you could draw them all out like that and then compare. That's perfectly fine. Another thing you could do is you could have assigned R and S to each of these three, and then gone around to all of these ones and assigned R and S on all of those. Bit more work, perfectly doable. Another thing you could have done is you could have built a model kit of the question I asked and then tried to match it up with the other ones. Another thing that would also be possible. Or another thing you could just go around is go, okay, I need the fluorine and the ethyl group to be cis to each other, and both those are trans to the methyl group. And so looking at that, the fluorine and the ethyl group are cis, they're both trans to the methyl, that one's kind of okay. Fluorine and ethyl group are cis, but they're not trans to the methyl. Everything here is cis together, so D is not going to work. E, fluorine and ethyl group are cis to each other. Fluorine and ethyl group are cis to each other. They are trans to the methyl group. That looks really promising. But then what you hopefully should realize is this is not, E is not the same molecule. Like, it's not even like a stereoisomer, it's a constitutional isomer. Stuff is attached to the wrong carbons. So if we look at F, or E, sorry, it's that. So the fluorine and the methyl group are across from each other, and the fluorine and ethyl group sort of have this 1-3 relationship, and that's not the same thing as that. It's a different molecule altogether. So when you're looking at these, you're trying to rule stuff out. Whenever you're looking at a multiple choice question, you're trying to rule out answers. So now, once we rule out the two that just aren't the same molecule at all, we're left with A, B, and C. Okay, now the question is, what is the most stable stereoisomer? Yeah, you're absolutely right. I did. Thanks. What is the most stable stereoisomer? Now, what you want is you want the biggest groups equatorial. In A and B, we've got two groups equatorial, the methyl and the ethyl. We have the fluorine axial. In C, we have the ethyl and methyl axial and the fluorine equatorial. Now, it's open book. You go back to your table of A values. You see that fluorine has a much smaller A value than everything else. So fluorine being axial is not a huge deal compared to anything else being axial. So under that logic, C is bad. The final exam, so I'm just seeing the chat, it's been a while. Kimia, the final exam questions are probably most similar to the assignment questions that I'm sending out than anything else. I would say that the most difficult assignment questions are more difficult than your final exam questions. I'm going to post a couple of practice final exams. And by practice final exams, I mean final exams I gave out in previous years. So they're very consistent with what you can expect. I am going to have to rework it a bit because what you'll see is in the practice exams I'm going to put out, there's a lot of questions which are provide the mechanism of this. I'm going to have many, many fewer questions like that. The main reason is a lot of that is copy paste. It's not a bad idea for more practice to look to Dr. Green's old exams, but they wouldn't be that reflective. We make it practice to not look at each other's evaluations. So I've never looked at his exams or his assignments. He's never looked at my exams or my assignments. We just don't want to start stealing ideas from each other. But I think a lot of the concepts are very similar. Yeah, I will. Okay, I'll do that in a second. Let's just finish this one off for now. Then the question for A and B is, are those both the thing we had? Now, the way to think about that is, let's just look at, what I want to think about is, are these possibly enantiomers or is it the same molecule? I want that to erase, and okay, it's just very resistant to erasing. That circle is not going to erase. So if I go from fluorine to the ethyl, that's clockwise. In A, if I go from fluorine to the ethyl, they're both up, that's clockwise. That's good. In B, if I go from fluorine to the ethyl, that's counterclockwise. Like not the other methyl. That's clockwise, that's counterclockwise. That tells me by definition that switching from clockwise to counterclockwise kind of thing is going from R to S or S to R. We're going to the enantiomer. So B is the enantiomer of A, and A is the same thing. Now I can confirm that by taking a look over at B over here and comparing B, what I drew with B, to what I drew over with the starting material, what you initially had. And it's really, really clear that those two are enantiomers. They are mirror images, like draw the mirror right between them, and they are mirror images of each other. And they are non-superimposable mirror images. So B and A are not the same thing, and B and the first thing are not the same thing. Whereas A is identical to the thing I drew. So the answer is A because we ruled out everything else. Okay, so let's talk about with the chair into and out of the page. So hopefully we're clear on what I mean by into and out. So this is, I call this out of the page, or into your face. I can't spell face. Where the idea is that that bond is coming out of the plane of the page into me, right? Yeah, A has the lowest energy of the ones that is equivalent to the starting material. Of all the ones in here, E has the lowest energy, but it isn't the same thing as what I drew in the starting material. It isn't it isn't the same molecule, but A has the lowest energy because A is lower than C. Which is the same molecule. B is a different molecule. D is a different molecule, and E is a different molecule. So only A and C are the same molecule, and A is lower in energy than C. Can I draw out D? Sure. I just, no, don't. It's recognizing my palm. Okay, now I've loaded up. Cortana will probably ask me if I'm making a presentation. Oh, did it not save my? Well, that would not be good. Oh, good. Okay. So D, we can draw the 6-membered ring. I'm going to put the fluorine here. It is coming up. The methyl group is coming up in that case, and the ethyl group is also coming up. They're all up. So how am I doing that? How do I know what's coming up and down? Come on, don't fail me now. Okay, out of the page, into your face, into the page, towards your feet. If you're saying like me, man, I'm starting to write like a 5-year-old. In my defense, I broke the tip of my stylus because I got very enthusiastic in office hours yesterday, and I threw my stylus across the room. So I can't write at an angle like I want to. So we're clear on what that means. Okay. Not seeing anyone saying no, so that's good. So you have a chair. On your chair, what you can think of is every line drawing to a carbon kind of looks like an arrow. And you're going to have these axials, which will be in the direction the arrow is pointing. So this arrow here, so this far right guy, is pointing down. So the axial is down, up, down, and they change. Next to that, so those are the axials in every single one of the carbons. The equatorials are going to be parallel to the two lines that are not attached to that carbon. So this equatorial here on this back carbon, this line here is parallel to that line and that line. This one here is parallel to that line and that line, and so forth. So if you need to sketch them in, you can sketch them in. Now, I'm just gonna throw some fluorines onto this molecule. I'm gonna throw lots of fluorines onto this molecule. There should be 6. Good. Now, for each one of those carbons, we're kind of looking at this with this like isometric view. We're not above it. We're not in the plane of it. We're kind of looking at the chair from slightly above it, off at an angle. If you played a lot, you know what, this is not going to work anymore. I used to say if you played a lot of RPGs in the 1990s, you'd be really used to this viewpoint. But yeah, that was a long time ago. So if you played a lot of retro RPGs from the 1990s, you'd be used to this viewpoint. And so we're slightly above it, but not directly above it. So in each case, one of those bonds is above the other one. And so I'm going to draw in blue. This equatorial is above the axial. On this guy, the axial is above the equatorial. The equatorial is above the axial. The axial is above the equatorial. Equatorial above axial. Axial above equatorial. So blue lines are on top of the red ones. The blue lines are on one side of the cyclohexane. The red ones are on the other side of the cyclohexane, not on the downside. So the blue is the up, the red is the down. So when we want to convert that into a hexagon, everything on the blue is coming out of the plane towards us, which in this case is 6 fluorines. Strangely enough, I bet you this molecule has never been made. So we got 6 fluorines poking us in the face. They're all on the top side of that cyclohexane because every one of those carbons is an up and down substituent, and it flips from being the axial substituent to being the up substituent. Next carbon over, it's the equatorial, then axial, then equatorial, then axial. And that's just the way the chair works. If you build your chair, you can sort of see that. And what we're doing is we're just kind of dividing it by, I thought I had a chair here somewhere. I do. Let me just try my video. If I let myself. Yeah, here we go. So I've got a chair. And on each one of those, you can sort of see this carbon here, the axial is above the equatorial. The next carbon over, the equatorial is above the axial. So I draw this as an up wedge, that is a down wedge. That would be an up wedge, that would be a down wedge. Up wedge, down wedge, up wedge, down wedge, up wedge, down wedge. And the whole thing is, when you're drawing the hexagon, you're looking like this. So your axials are quite clearly pointing towards you, like the 3 axials. The equatorials, though, are clearly above the down equatorial, the down axial. So you have 6 above the plane of the cyclohexane and 6 below the plane of the cyclohexane. And each carbon has 1 above, 1 below, and whether it's axial or equatorial switches between each carbon. So everyone who was asking about talking about this kind of thing, did I answer your question? Is there something that's not clicking there? And there very well might be. Cool. Okay. I should label this video how to read a chair. Okay, awesome. I'm really sorry. I probably should have taken some more time earlier. So I'm really glad somebody stopped me and mentioned that. We've got 10 minutes left. Anything else that anyone particularly wants to talk about? Yeah, the blue lines are all going to be wedge bonds. They're all coming up towards you. Yeah. Because they're all above the plane. They're all the top ones on each individual carbon. Can I go back to chair C? Yes, I certainly can. Well, I can try. Okay, so chair C. Yep, they're a mix of axial and equatorial. Because on a given carbon, like look at it, this axial here is clearly above this equatorial here. This equatorial here is clearly above this axial here. Like axial doesn't mean up. Axial means axial. It means it's vertical. But that flips. This axial's up, that axial's down. This axial's up, that axial's down. Like they go, every carbon has an axial, but every carbon is two neighboring carbons in a chair have their axial pointing in a different direction from it. Like that's just how tetrahedra work. You stick them into the chair, you get this. If you are still confused, please, 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 please build your model. Yeah, I think this time, oh shoot, I think I have the settings. Oh no, I have no idea, we'll see. I think I have the settings so that it should have like a full-size video next to this of that. But we shall see if that's the case. Can I do a quick one? Yeah, let's. Okay, so Nulia wants a cyclohexane with bromine chloride. Kareem wants an RRS. Let's do. Yeah, Rita, that's exactly it. It's just a Markovnikov without using an acid. It seems like an awful lot of trouble. Yeah, flipping a chair gives the same up or down result. You just change every equatorial to an axial and every axial to an equatorial. But everything that was up stays up when you flip the chair. And everything that's down stays down when you flip the chair. It's just every axial has become equatorial, every equatorial has become axial. When I flip my chair, I'm not turning my chair upside down. I am, which would actually be still a good definition of flipping the chair. I'm rotating these two bonds. I'm flipping what's making the chair. And so you notice I'm not turning it upside down. All I'm doing is every axial is becoming equatorial, every equatorial is becoming axial. And it's kind of mesmerizing if you're doing it in front of yourself. I skipped Harjit's question. That's because I probably didn't see it. Harjit. Okay. For C, how can it be the same? Because it's upside down. Because this chair is the same as that chair, it is just upside down, right? I just changed my perspective. I did not change the molecule. So if we take C, and what I do is I take that and I flip it like a pancake. So I literally, take it and do that. Pancake flipping. So if we flip it like a pancake, and I could pretend I don't know anything about rap songs and talk about flipping things like pancakes. Because what's wrong with pancakes? That's the molecule. I took that molecule, I flipped it over. That's the same molecule. All I've done is rotate it. Now, no, I guess it's the enantiomer. Go figure. Okay, so C would have been wrong because it would have been the enantiomer. It was wrong because it wasn't the most stable conformation, but it's also wrong because it's the enantiomer. But it's not wrong because the fluorine's upside down, because you can still flip things around. Yeah, you just rotate. I can rotate this as much as I want, right? As long as I don't break any bonds, this is all the same molecule. Like this molecule is constantly wiggling and moving, and everything is changing, and all the bond angles are constantly changing. But as long as I don't break any bonds, this is the same molecule. As soon as I break a bond, I can make a different molecule. But rotating and flipping things does not make it a different molecule. Okay, let's assigning R and S. I'll do C was an enantiomer of the original molecule, yeah. We're gonna, Nulia, we're gonna do some more of the alkene stuff. We're gonna take a little break from it, but there's more examples, and we're gonna be coming back to it. So I'll leave that. I wasn't gonna talk a lot more about RNS in this course, so I'll spend a little moment doing one of those. So there's no, you can sort of say, oh God, this molecule looks complicated, but no molecule is particularly complicated. So let's stop sharing. I'm going to exit, keep everything. And those of you who need to run off to something, run off to something. Those of you who don't, can stay, I guess. And I'm just going to do one example with a few different cases. So I'm looking at one of my favorite molecules. I'm working without a mouse, and it's very confusing to be using a touchscreen. Oh, come on. Okay, I'm going to start sharing again. Okay. This is a suitably complex molecule. So this is the pufferfish toxin, tetrodotoxin. Just want to make sure I have the chat window open because I think I've just closed it. So this is pretty fancy. So what we can do is, okay, so where are the stereocenters? So any carbon is attached to 4 different things. We can quickly, you know, not a bad exercise. Quickly go through it. It's got a lot of them. Actually, all the carbons are stereocenters. Now, complex. How do you assign RNS to this? So what we do is we go atom by atom. That's all we worry about. So let's pick one at random. This guy. There's actually some really tricky ones on this because I think I've actually used this as an exam question in the past. So let's just look at this guy, okay? And I'm going to resketch it over here. What that effectively means is that. With the one that's in the ring going back, being back. Now I just need to assign priority. Okay, looking at that carbon, there's no hydrogen, so we have no easy number 4, but we do have an easy number 1 because this carbon is attached to an oxygen. So the down one is number 1. Look, it's kind of like I'm reducing this thing to its component parts. I'm not treating it like a whole molecule. I'm just looking at the specific thing. There is quite clearly a number 4, though, because both of these carbons are obviously attached to longer chains. Both this carbon and this carbon are longer chains. This carbon is going to run out of space in that OH. So that's going to be lighter. Now, what we can look at is these 2 carbons. They're going to be tied. Which one of these is 2? Which one of these is 3? Okay, you have to follow the heavier chain. So the heaviest thing this thing's attached to is the oxygen. Heaviest thing this thing's attached to is an oxygen. Okay, that's a tie. Next heaviest thing this thing's attached to is a carbon. Next heaviest thing this thing's attached to is a carbon. That's a tie. Next heaviest thing this thing's attached to is a hydrogen that's not drawn. Same thing here. That's a tie. Everything's a tie. Okay, now we need to go to the tiebreaker, which is the next heaviest atom on the chain, which is the oxygen. Those are both oxygens. That's a tie. Both of those oxygens are now attached to the same carbon. Automatically now we are completely tied on those things along this route because they're going to read this the same way each way, right? Like each of these is going to be tied the whole way along because they've joined up to the same atom. This question isn't from anything. I've just made up a question. I was asked, can we look at RNS in a complicated molecule? So those are complete ties. So what we're now going to do is try and go, and we tied because we ended up at the same atom. So when we look at the other root, okay, well, the next biggest thing these things are attached to is the carbons. So this is attached to a carbon. This is attached to a carbon. Both those are carbons. This carbon is attached to an oxygen. This carbon is not. This chain here is heavier because it gets the tiebreaker first. Now I can go around each of these carbons and do that. This is a complicated molecule, but just because it's a complicated molecule doesn't make it any more complicated because you're looking at each of these atoms in isolation. You just follow the rules. Stability and decalins. Decalins don't really have a lot of choice. You can't ring flip a decalin. So if you have a transdecalin, you got a transdecalin. If everything is axial, there is no choice. You can't ring flip that. Yeah, the tetrodotoxin is blurry. I know, I'm sorry. It's because I blew up a big picture. But for a transdecalin, this cannot ring flip. There's no choice. A cisdecalin can ring flip, and so you minimize the axials. But a trans can't. And we're already a few minutes over, so I'm going to call it a day here. And on Friday, we're going to start talking about some carbonyl chemistry, if the world hasn't ended by then. And next week, we're going to continue carbonyl chemistry. And if anyone does have questions, that is what the office hours are for. They're 3 hours a week. Much better attended this week, which was really awesome to see some people. Some people just come and hang out and listen into what people talk about. Yeah, I didn't actually end up assigning it, did I? This is S. No, it's yes. Yes, it is. Yes, it is. Because what I can do is I can, if you can't see why that's S, take this carbon one bond, use that as an axis of rotation, and then swap 4 for 2, 2 for 3, and 3 for 4. You're just kind of spinning the propeller. So you do a rotation. 3 goes where 4 was. 2 goes where 3 was. And 4 is now in the back. And that's S. Yeah. Exactly, Alexis. Okay. Have a really good rest of your day. And I will see you on Friday. Once I figure out how to stop recording.